Hello everybody, and welcome to exercise 1 on page 78. Let's take a minute to read this question together. So define T, going from the set of all 2 by 2 matrices to P2 of R by this long formula. And they'd like us to find bases for the range of T and the null space of T. Okay, and our approach to this problem is going to be the same as the approach that we used in the last few examples. We're going to first find a matrix for this transformation. We're gonna find the range and the null space of the left multiplication operator, and then use that calculation to figure out the range and the null space that we really want. Okay, so to get that process started, we need a matrix. Okay, and that means that we need to choose bases for our domain and our codomain. Generally, you try to choose the nicest bases that you can. So how about if we choose just the standard basis for both of those sets? All right, so that's going to be our first line here. Let's let beta and gamma be the standard ordered bases for the set of 2 by 2 matrices and P2 of R respectively. Okay, just to get us started here. All right, and so to find our matrix, we need to take the basis vectors for our domain. Remember what the standard ordered basis for M2 by 2 of R looks like. So it looks like the matrices 1, 0, 0, 0, 0, 1, 0, 0, and so on down the line. Okay, we're going to substitute those in one at a time and just see what we get out here. Okay, so let's start with the first of these calculations here. So T of 1, 0, 0, 0, we're going to go up and use this formula. Notice that to do that calculation, A is going to be 1, and B, C, and D are all going to be 0. So if we go to our output, substitute in 1 for A, 0 for the other variables, what we'll get out is 1 plus x plus 3x squared. Okay, and similarly, T of 0, 1, 0, 0, now it's B that's 1, and all of the other variables are 0. So if we go up here again, substitute in B equals 1 and 0 for the other things, you can check me. Note that we're going to get 2 plus 2x plus 6x squared out, and we just keep doing this. Okay, so I'm going to go ahead and fill in the last two calculations. You can confirm that these calculations are correct. Okay, and now we're in a position where we can write down the matrix of T, okay, relative to these bases. Since we chose the standard basis, it's not too difficult to do. We really just need to pay attention to the coefficients. So we've got, let's write an imaginary 1 there. Okay, 1, 1, and 3, that would form the first column of our matrix. Okay, and then if you go down the line, we get sort of the same thing happening with all of these calculations. So then 2, 2, 6, 0, 1, 2, and then finally 1, 0, 2. Okay, and just for the sake of notation, I'm going to give that matrix the name and call it A. Okay, we'll refer to that kind of as we go through the problem here. Okay, and so what we'd like to do is to find the range and the null space of the left multiplication operator. And to do that, we'd like to row reduce this matrix. Okay, so let's recopy it. 2, 2, 6, 0, 1, 2, and then 1, 0, 2. Okay, and if you do row operations on this, okay, you can either do this by hand or on a calculator. Here's what you might end up with. 1, 2, 0, 1, 0, 0, 1, negative 1, and a row of zeros. Okay, again, that's what you get after you do row reduction. All right, where are the pivot positions here? Well, let's see, it looks like we've got 2 of them in this case. And at this point, we're ready to go through the process we've been talking about to write down the null space, bases for the null space and the range of the left multiplication operator. How about if we start with the null space? Okay, that's really talking about the set of solutions to the system AX equals 0, Okay, so to get started on that, locate our free variables. Let's see, looks like we've got two columns that don't have pivot positions, so it would appear then that x2 and x4 are our free variables. So let's give those names. x2 is t, and x4 is u. And we can go up to our matrix and figure out what the other two variables are. Okay, so maybe starting with the second row there, if we read that off, kind of put a 0 in on the right-hand side, we're going to get x3 minus x4 equals 0. If we take that and solve it for x3, we're going to get x3 equals x4, and we know that x4 is u. All right, and then up to the first equation, if we read that off, it looks like x1 plus 2x2 plus x4 equals 0. Okay, if we solve that for x1, we're going to get negative 2x2 minus x4. Okay, and let's see, x2 is t and x4 is u, so we're going to get negative t minus u out of that, it looks like. Okay, and so we can now write down what our null space looks like. Okay, it's going to be the set of, let's see, x1 is negative 2t minus u, x2 is t, and so on down the line here. Okay, so we're going to get that. All right, and let's go ahead and pull that apart. Okay, I think we skipped this step in some of our calculations in previous examples. Let's go ahead and write it out one time. Okay, so if we break that apart, we can rewrite it like this. Okay, I just confirm that that's right. All right, and I think with the calculations that we've done, we're in a pretty good position to go ahead and write down a basis for the range and the null space of our left multiplication operator. All right, let's do that on the next line here. Let's start with the range. Okay, so basis for the range of L of A there, what we're interested in is the pivot columns of our matrix A. Okay, so looking at our row reductions, we can see, that the first and the third columns, those are our pivot columns, and so we're interested in the first and the third column of our original matrix A. All right, so let's go ahead and write those vectors down. First column looked like 1, 1, 3. Okay, the third column looked like 0, 1, and 2. Okay, good. And then what about the basis for the null space of L of A? All right, well there we can kind of see from our calculation just above here, the null space has been written as a linear combination of those two vectors, and so those two vectors should form a basis. Negative 2, 1, 0, 0, okay, and negative 1, 0, 1, 1. Okay. So we find ourselves then kind of in the intermediate step here. We've got a basis for the range in the null space of LA. We'd like to translate that now into a basis for the range in the null space of T, the actual operator that we started with. Okay, and the key again is to interpret these vectors that we just found as coordinates. Okay, and if we start with the basis vectors for the range of L of A, okay, we'd be talking about the basis for the outputs, okay, for the codomain. If you look back up at our work, the basis for our outputs, we called that gamma, and so we would be interpreting then those two vectors as being gamma coordinate vectors, okay? And so going down, let's see, can we sneak this in here? Yeah. Looking at our answer, this line up here, our basis for R of L of A, should help us to find the basis for the range of T. Okay, so let's do this one at a time, starting with 1, 1, 3. Think of 1, 1, 3 as being coefficients on the basis gamma. That means we'd be looking at the 1, 1, 3 and thinking of it as 1 plus 1x plus 3x squared. Let me be consistent with my colors here. So 1 plus 1x plus 3x squared. that's our first actual vector in the basis for the range of t. Okay, and then similarly, 0, 1, 2, we'd be looking at that and thinking 0 plus 1x plus 2x squared, okay, which we can write as just x plus 2x squared. Okay, and so we have a basis for r of t. Okay, now what about a basis for the null space of t? Well, now we're going to look down here and remember that the basis for our inputs, for our domain, we called beta, and so we're thinking of these vectors as being beta coordinates. So if we start with negative 2, 1, 0, 0, we're thinking of those as coefficients on the basis beta. That's a basis that involves matrices. And so the corresponding matrix there would look like negative 2, 1, 0, 0. Okay, now if you're wondering where that came from, okay, all we did there was we took the numbers in this coordinate vector and put them in front of each of our basis vectors. So if we wrote it out, it would kind of look like this. Negative 2 times our first basis vector, plus 1 times our second, okay, plus 0 times our third, and so on. Okay, and you can do that calculation and confirm that it gives you this matrix up here. All right, and then similarly, to get our last one, we'll look at that, interpret that as coordinates. That's going to correspond to the matrix negative 1, 0, 1, 1. Okay, and those two matrices would form the basis for n of t. Okay, and so our answer to the whole question that was asked would be this, that I'm circling right here.